Hi everyone, and welcome to the last class on number system. So in the last 5 classes we have covered quite a fair bit. My name is Nishant, and with me in the first class we went through the classification of numbers, we looked at rules of divisibility, and we looked at sum of natural numbers. In the second class we covered all concepts related to HCF and LCM, and we looked at few models as well, 3 models for LCM and 2 models for HCF. In the third class, we covered all concepts related to factor of numbers. Okay. In the fourth class, then we went on to look at cyclicity of numbers. And through cyclicity, we found out the last digit and the second last digit. And in the last class, we looked at all concepts related to factorials. And now in this class, which is the last class, I'm going to take upon the most difficult or the most complex set, which is remainders of numbers. So numbers, when you divide, what will be the remainder? So we are going to look at that. Hope you have attended, watched, noted down all the previous classes. In case you have missed any of them, please go through that, complete that, and then come to this class, because there will be references, connections, and usage of what we discussed in the previous classes. Okay, so let's get moving. Fine. So just to do a recap of what we had discussed some time back, dividend we all know is equal to divisor into quotient plus remainder. Okay, so the basic formula, and this we had discussed multiple times, that dividend is equal to divisor into quotient plus remainder. Normally dividend is larger, so we mention it by capital D, and divisor is smaller, so we mention it by small d when we write this formula. Okay, and normally your remainder will be greater than 0. Though we have a concept of negative remainders also, which I'll touch upon very soon. Okay. If the dividend is fully divisible by the divisor, then the remainder will be 0. And then in that case, the divisor is also called a factor. Okay, so we had done factors and all concepts related to factors in the third class. If the dividend is less than the divisor, let's say I have 3 getting divided by 5. So obviously in this case, no division will happen. Your quotient will be 0. Okay. And whole of 3 will become your remainder. Okay. So in case the dividend is less than the divisor, then the remainder is the dividend itself. For example, same example, 3 divided by 5, 3 is the remainder. Then second important part is the remainder should always be calculated in its actual form. For example, if 10 is divided by 4, so a lot of times we are in the habit of writing it as a fraction, 10 by 4, where 10 is the dividend and 4 is the divisor. But a lot of times what mistake we make, 10 by 4, we reduce it to 5 by 2. Okay, and we say the remainder is 1, which is wrong. Okay, this is a division, this is not a fraction, so you can't simplify it. If 10 is getting divided by 4, 10 should get divided by 4, and you should not be simplifying it. Okay, so this is what will happen. 10 will be equal to 2 into 4 plus 2. Okay, so this is what will happen, and you should not reduce it or simplify it. Okay, then I hope you remember the divisibility rules which we discussed in the first class, and especially one rule is very important. When we had discussed that to check the divisibility of a number by a power of 2 or a power of 5 or a power of 10, when they are of power n, you need to look at last n digits. Do you remember that? For example, if I give you a number 1, 2, 3, 4, 5 and I ask you whether it is divisible by 2 or not, you need to look at 5. For 4, which is 2 square, you need to look at 45. Okay, for 8, which is 2 cube, you need to look at 345. Same also applies for 5. Same also applies for 5 square. Same also applies for 5 cube, right? Okay, so in the first class we had discussed that you check this to check whether it is divisible or not. I'll just extend that logic a bit. It will also tell you what is the remainder when it is divided. For example, 2, when you divide 5 with 2, you see that you get a remainder of 1. Okay, so in case of 2, you will get a remainder of 1, and in case of 5, you get a remainder of 0, that means it is fully divisible. So it tells you whether it is divisible or not, and in case it is not divisible, it will also tell you the remainder. So for example, 2 square 4. So 45 when you divide by 4, you will get a remainder of 1. And similarly 45 when you divide by 25, you will get a remainder of 20. Okay, 2 cube is 8. 345 when you divide by 8, 320, 344 will be divisible, you will get a remainder of 1. And this is 125. So 345 when you divide by 125, you will get a remainder of 95. Okay, so when you divide this, if you get remainder of 0, that means it is fully divisible, and if it is not divisible, just divide that and that gives you the remainder as well. Okay, so this is for powers of 2, 5 and 10. Also, I hope you remember the rule for powers of 3. Powers of 3, the rule was sum of the digits. Okay, so let's extend this number to 1, 2, 3, 4, 5, 6, 7. Okay, so let's say I have this number, and if I want to check the divisibility by 3, if you remember, we were checking the sum of the digits. Okay, so sum of the digits, if you check, it will be 28. So this is 28. So 28 is not divisible by 3. That's what we had learned. Now we'll go one step further. 28 divided by 3 gives you a remainder of 1. Hence the remainder for the number also will be 1. So not only it tells you whether it is divisible or not. In case it is not divisible, you divide that sum by 3, you get the remainder as well. Same for 9. 9, you divide 28 by 9, you again get a remainder of 1. So for powers of 3, the sum divided by that number will give you the remainder as well. Okay, so powers of 2, powers of 5, powers of 10, powers of 3. This method works very beautifully and it can be used there. Fine. Okay, let's move on. So what we will do today is we are going to look at some simple rules to some very basic concepts. For example, this is the rule of divisibility which we have used. We'll look at some expansions also, and we are going to discuss some very important theorems also. Okay, because as I told you, remainders is one of the most complex chapters or concepts of number system, and you have to be very, very thorough with this. So we'll look at all possible ways, and by the end of this class, you will be able to find remainder of any number. That is my guarantee to you. Okay, so let's say the question let's do one question before we move on. So what is the remainder of 703488 divided by 11? Now for 11, there is no rule. Rule of divisibility, you remember, it is the sum of the digits at the odd places, sum of the digits at the even places, and you subtract them. You either get 0 or you get a multiple of 11. That tells you whether the number is divisible or not. That does not tell you the remainder. So for remainder by 11, we'll have to manually divide. And since this is a small number, we'll manually divide. But as we go along, I'll give you certain better methods or formulas, but that normally we use for bigger numbers. This is very simple. So let's do it manually. 703488 divided by 11. You have 6 times 66. Then you have 43. So 3 times 33. You have 10. 104. So 9 times 99. Then 58. 5 times 55. And then 38. 3 times 33. Your remainder is going to be 5. As simple as that, we can find the remainder is 5 in this case. Just in case you want to check the even and odd. Okay, so 7 plus 3 plus 8 is 18. And 0 plus 4 plus 8. 0 plus 4 is 7. 7 plus 8 is 15. So you get 18 and 15. The difference is 3. Which tells you that it is not divisible by 3, but you can see that it does not give you the remainder. So this rule, divisibility rule, does not give you the remainder of 11, remember. Okay, it gives you for powers of 2, 5, 10 and 3, but not for 11. So 11 we'll have to check it manually. But there's a formula that I'll tell you just in a bit. Okay, so I hope this is clear. This is being done through the standard method. Okay. Then I told you just now, let me introduce to you the concept of negative remainders. Remainders theoretically are always non-negative. So remainder can be 0 when the number is fully divisible, or remainder can be a positive number smaller than the divisor when the number is not fully divisible. But We use the concept of negative remainders, especially to find the remainders, because it reduces our calculation quite significantly lot of times. Okay, so what happens here is, let's say 30 is getting divided by 4. Normally it will get divided 7 times. You'll have 28 and you'll have remainder of 2. So the equation will be 30 is equal to divisor, which is 4, into quotient of 7 plus 2. Now this finally is the equation, right? This equation I can also write as 4 into 8, 32 minus 2. Okay, so this is also possible. Now when you write it like this, basically if you see, this is your dividend, this is your divisor, this is your quotient, and this is your remainder. Okay, so theoretically it is possible, equation wise it is possible. Okay, so remainder here in this equation is minus 2. Okay, which is fine, which is not a problem. The only thing is you cannot give minus 2 as a remainder in any answer. So when we get a negative remainder, all that you have to do is to that negative remainder add the divisor. What was the divisor? The divisor was 4. So add the divisor. Okay, and your remainder will become plus 2. Okay, this is all that you have to do. So whenever you have a negative remainder, you just have to add the divisor. And remember, when you add the divisor, basically, and let's understand equation wise what we are doing. 30 is equal to 4 into 8 minus 2. This will be changed to 4 into 7 plus 4 minus 2. This is what we do. Okay, so basically the quotient gets reduced by 1, and this will give you 4 into 7 plus 2. Okay, this if you see is exactly same as what we had here. Okay, so whenever you get a negative remainder, you add the divisor to it, and in the process what happens is your quotient also reduces by 1. Okay, your quotient reduces by 1. Though we are not bothered with the quotient most of the time. So here if you see, when we had a negative remainder, my quotient was 8. When it was converted to a positive remainder, your quotient has become 7. Okay, so your quotient will reduce by 1 when a negative remainder is converted to a positive remainder. But you should not really bother. But very, very useful in a lot of questions. Let's look at one question, for example. What is the remainder when 62 into 63 into 64 is divided by 66? Okay. Now, obviously remainder in the first case is 62, second case is 63, third case is 64. Okay, but they are getting multiplied. These numbers are getting multiplied. So here I don't have a dividend. I have dividend 1 into dividend 2 into dividend 3 getting divided by a divisor. What happens when you have multiple dividends or you have dividend into parts? Let's look at the concept related to this first. Yeah. So addition, subtraction and multiplication of remainders. Okay, so understand this and then we'll go back to that class, that question. If x, y are natural numbers and the remainder of x divided by n is this remainder, y divided by n is this remainder, and so on, then the remainder of x plus minus or multiply y plus minus or multiply divided by n is same. So basically looks complex but very simple. Basically whatever you do to the divisor, to the dividend, you add dividends, subtract dividends or multiply dividends. Whatever you do to the dividends, the same thing you can do to the remainders as well. Okay, so it means when you have something like this, you find out the remainder here. Let's say it is R1. You find out the remainder here. Let's say it is R2. Okay, and let's say dividend 1 and dividend 2 are getting multiplied. So net in your answer, remainder 1 and remainder 2 will also get multiplied. If dividend 1 and dividend 2 are getting added, your remainder 1 and remainder 2 will get added. If dividend 1, dividend 2 are getting subtracted, your remainder 1 and remainder 2 will get subtracted. So whatever operation you do on the dividends, the same operation you can do on the remainders. Okay, that much is enough. Then we'll come back to this in a bit. Meanwhile, let's solve this question. Okay, so That means I can divide 62 by 66 separately. Whatever is the remainder that I can get. Okay, so remainder of this I can multiply with remainder of 63 by 66, and I can multiply with remainder of 64 by 66. Okay, so this will be my answer, because the dividends are getting multiplied, the remainders will also get multiplied. As simple as that. Now you can see that in first case the remainder will be 62, second case it will be 63, third case it will be 64. So your answer will be 62 into 63 into 64. This will be the remainder, and since it will be bigger than the dividend, you will have to divide it again. But this can be a long question, long solution. So instead of doing this, we take help of negative remainders. 62 when divided by 66, I can say it gives me a remainder of 62, or it gives me a remainder of minus 4. So instead of 62, I'll say my remainder is minus 4. In the second case, my remainder is minus 3. And in the third case, my remainder is minus 2. I can say this also. So minus 4, minus 3, minus 2, 3 minus, so you'll have a minus. 4 into 3 is 12, 12 into 2 is 24, my remainder is minus 24. Okay, now your remainder is negative. So when remainder is negative, what did I tell you that you do? You basically add the divisor to it. So 66 minus 24, that means your remainder is going to be 42. So this is the answer. So it can be solved as simple as this, by taking help of negative remainders, which you can see is a very, very useful concept here. Fine. So I hope we are clear here. This is one very simple application of negative remainders, and it is useful a lot of times, and we'll solve some more questions where we'll be taking negative remainders. Okay, fair enough. Let's move to the next question. What is the remainder when 299 to the power 33 is divided by 100? This question I think we had done in one of the earlier classes also, where we found out the last two digits of 299 to the power 33. Now last two digits of 299 to the power 33 would be same as the remainder when 299 to the power 33 is divided by 100. Okay, so essentially both the questions are same. Now I want to use the concept of negative remainder here. One thing that you must remember is your binomial theorem. In binomial, if you remember, we had discussed this, that if you have a plus b to the power n, this expansion is, your first value of this term will be nc0, a to the power n, b to the power 0. Then nc1, a to the power n minus 1, b to the power 1. And it will go on like this. The second last term will be ncn minus 1, a to the power 1, b to the power n minus 1, and the last term will be ncn, a to the power 0, and b to the power n. Okay, important here to notice is that the last term will not have a. It is a to the power 0, which means 1. So last term will have only b. Okay, and the first term will not have b, it will have only a. Okay, so 299 to the power 33, if I write it as 300 minus 1 to the power 33. Okay, and you expand this. Then all the terms from the first term to the second last term will have some power of 300 in it. Okay, because this is a and this is b. So you can see the second last term also has a to the power 1. That means the second last term will have 300 to the power 1. And the terms before that will have higher powers of 300. That means all of them will be divisible by 100. Okay, so it's only the last term that will give you the remainder. All other terms will get divided, right? So 300 minus 1 to the power 33 divided by 100. All terms except the last term. Last term will not get divided. And what is the last term? Last term is 33C33, 300 to the power 0 into minus 1 to the power 33. Okay, this divided by 100. Now 300C33 is 1. 300 to the power 0 is also 1. So essentially what you get is minus 1. Minus 1 divided by 100, your remainder is minus 1. Okay, so you can see that you're getting a negative remainder here as well. And minus 1, your divisor is 100. That means effectively your remainder is 99. So answer is third choice. So here also we are using the concept of negative remainders. Okay, and this binomial expansion is very important. We'll discuss this a bit more in one of the subsequent slides, but this is something that you must remember. And why it struck us that we should use 300 minus 1, because you can see that your divisor is 100 and the dividend is so close to a multiple of 100. It is 300 minus 1. So automatically that is something that should strike you, and hence this can be done in this way. Okay, great. Let's move on. Then we use LCM HCF concept also in remainders. Okay, and I'll do some examples so that you understand this. For example, what is the greatest number with which, when we divide 55 and 37, remainders are 7 and 5 respectively? Does this question ring a bell? Did we do this question like this some time back? What is the greatest number? First, the question is the greatest number. So it has to be HCF, right? With which, when we divide, when we divide. So these are your dividends, right? And these are your remainders, right? And you can see that in HCF model, we know the dividend, we know the remainder. So this is nothing but HCF model 1. HCF model 1, you know the dividend, which is 55 and 37. You know the remainder, which is 7 and 5. So if you remember, what we used to do is dividend minus remainder, that is 48 and 32. You will find HCF of that. So HCF of 48 and 32 is 16. So the highest possible number is 16, and you can check 16 divided by 55 divided by 16 gives you remainder of 7, 37 divided by 16 gives you remainder of 5, so answer is 16. Okay, so just to do a recap, because those concepts are also used to find this. Similarly, find the greatest number, again HCF, that divides these numbers, leaving the same remainder. I hope you remember, this is HCF model 2. Okay, and in HCF model 2, what did we do? We used to subtract the dividends. So D1 minus D2, D2 minus D1, D3 minus D2. So when you subtract them, 65 minus 05 is 60, and 46 minus 13 is 33. So 33, 60, and third minus second, 05 minus 65 is 40. 68 minus 46, 46 is 22. This is what we get, and then we have to get the HCF of them. Okay, so 10 is common, so let's take 10 out. Then 2 is common, so I have 112, and I have 168, right? One more 2 is common, 112 will become 56, and 168 will become 84. One more 2 is common, 56 will become 28, 84 will become 42. One more 2 is common, 28 will become 14, 42 will become 21. 7 is common, this will become 2, and this will become 3. So this is the HCF, which is 10 into 2, 20, 20 into 2, 40, 40 into 2, 80, 80 into 2, 160, 160 into 7. That will give you 800 plus 320, 1120. So 1120 is your highest possible number, right? And with 1120, when you divide 1305, you get 185 as the remainder. Okay, and it should be the same in every case. So 185 is going to be your remainder. So this is HCF model 2. And the third one, what is the least number? Least number, that means we are talking of LCM. When divided by 42 and 70, leaves remainder of 4 in each case. Remainder is same, so this is your LCM model 1. And LCM model 1, the answer is LCM of 42 and 70k plus 4. right? I hope you remember that. Okay, so 42 and 70, what will be the LCM? 210. So 210k plus 4 will be the answer. Okay, and the least number is when you put k is equal to 1, so 214 will be the smallest possible number. Okay, so just a brief recap, but these concepts also are sometimes used. Okay, let's look at the next one. What is the greatest 4-digit number that is completely divisible by this? 15, 25, 40 and 75. What will you do here? There is no remainder left. So this is LCM model. We can say this is LCM model 1. Okay, LCM model 1, where your remainder is 0. That is also same. Completely divisible means your remainder is 0. So answer is nothing but LCM of 15, 25, 40 and 75 into k plus remainder, but that is 0. Okay, so as I had discussed, I'll prefer that we check for multiples of 75. Now 75 is already a multiple of 15 and 25, so really you have to bother about 40. And for 40 you have to look at something that ends with a 0. So 75 odd multiple will not work, you'll have to check for even multiple. So 75 into 2 is 150. Now let's check for multiples of 150. 150 into 2 is 300, 300 does not divide 40. 150 into 3 is 450, 150 into 4 is 600, 600 works. So the HCF is going to be 600. Okay, so my answer is 600k. Okay, the question is greatest 4-digit number, so k can be 16. If I do 600 into 16, I'll get 9600. So this is the greatest possible number that satisfies this condition. So very, very simple application of LCM model 1. Okay, let's look at one more question. A certain number when divided by 899 leaves remainder of 64. Okay, so this is the divisor, this is the remainder. So D is equal to 899Q plus R. This is my divisor, this is my dividend. Okay, what will be the remainder when the same number is divided by 29? Now my problem is that I do not know the dividend, but this number now is getting divided by 29. Okay, this remainder is already known to me. This remainder is 64. And this kind of question again is a very common question and it has been asked in different forms. So just understand this carefully. So this is 64. Okay, now when this number I divide by 29, first you'll have to check the relation between 899 and 29. What is here? 829 into 30 is how much? 290, 580 and you'll have 870. Okay, and if you add 29 more, you'll get 899. So basically 899 is nothing but 29 into 31. Okay, so when you divide the dividend by 29, whatever is 899Q, you don't need the value of Q because 89 itself is divisible. So that means this part will give you remainder of 0. So I'm only bothered about this part. Okay, 64 divided by 29. When I do that, my remainder is going to be 29 into 2 is 58. So my remainder is going to be 6. Hence your answer is 6. Right? That's good enough. And most of the times you will get the divisor a number which will be a factor of 899. So the first part in most of the questions will get cancelled fully. It will not leave any remainder. It will get fully divided and remainder will come only from the second part. Okay. So these kind of questions can be done very easily using your first principles, using your dividend is equal to divisor into quotient plus remainder concept. Okay. Great. Let's move on. One more number. Two numbers A and B are such that when divided by 6, they leave remainders of 4 and 5 respectively. Okay, so A and B when divided by 6, so 6Q1 plus 4, and the second one is 6q2 plus 5. These are my numbers. Find the remainder when a square plus b square is divided by 6. Okay, so now I am dividing a square. So a square will be square of this, b square will be square of this, which will be how much? 36 q1 square plus 6 into 4, 24 into 2, 48 q1 plus 16, and b square will be 36 q2 square plus 16 by 30, 30 into 2, 60, 60 q2 plus 25. Okay, when I add a square plus b square, I get 36 q1 square plus 48 q1 plus 16 plus 36 q2 square plus 60 q2 plus 25, right? And this is divided by 6. So you can see which parts will get fully divided. Whichever are multiples of 6, this is a multiple 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 of 6. So all these are multiples of 6. What is left now is 25 plus 16, which is 41 divided by 6, which will give me remainder of 5. So your answer would be 5. So you need not really know A and B. You can still figure out using something very similar that we had done in the previous part, that you write down this into divisor into quotient plus remainder, and then you will see which parts are divisible, which parts are not, and that will give you the answer. Okay, so very, very simple here also. So far, I hope you are with me, you have understood the concepts, okay, and we are taking it gradually. We'll look at some more variations as we move on.